Hi, thanks for being here. We're gonna now follow up the theoretical lessons that you have just followed on the thermodynamics on multi-phase mixture, and we will be seeing some example and application, mostly using a software that has been developed specifically to solve the equilibrium thermodynamics of two-phase magmas with volatiles. So you have seen the theory, and now I'm going to show you some examples and how to use the software that we have been developing that is called SolveCAD. So the first lesson, we will tell you how to download, install, and run this software. Software that is specifically tailored for computing the fully non-ideal thermodynamic equilibrium between a water and CO2 gas phase and a silicate melt of a general composition expressed through its 10 major oxides. Here's a recap of the equations that you have just seen. So basically what SolveCAD calculates are the weight fraction, the composition of the two fluid components that we have, that are water and CO2, into the melt and gas phases. So how do we install and run SolveCAD? First of all, we need to download it, and we will do it from the website of the Volcanodynamics Computational Center, that is basically a hub for some relatively fast codes that have been developed here at INGV in Pisa to perform different kinds of computation, including SolveCAD here. We will download the application. It's a zip file, as you see. I have downloaded it already, but you can safely download it. And it will be saved in the folder that you have decided. As a zip file, so then you will need to run and unzip it. So unzip solvecad.zip, and then we can take a look at the files that are in the folder that has been created. So let's see if we can do that. You see the zip file, we can unzip it. We can replace all of them, yes. So now we can take a look at the directory there and see what's in there. You see that there's a bunch of files. The first one, SolveCAD, is the executable that we will use to run calculations. Then there is a license that is a very simple license that will basically tell you that you can freely use the software, but you cannot redistribute it, and you need to cite its source. And then there is a manual also that's called the quick manual. It's easy, and it tells you all the details on how SolveCAD needs to be run. Both in this version that you have here, but we also have an online version, as well as a routine that can be included into any other software that you may want to write for your research activities. And then input files, the two main input files for SolveCAD that are sw.data and swinput.data. These two files basically look like this. They are simple text files where we input all the data that SolveCAD needs to run the calculations. So basically, they are the condition of pressure and temperature, and the composition of the melt, and the water and CO2 content of our magmas. SW instead contains some details on how the calculations need to be performed. So let's take a look at them. First, sw.data, that contains all the main input data in terms of thermodynamic quantities and melt composition. Each line represents one set of input data, and it will be one calculation for SolveCAD for each line. And we have pressure, temperature, water content, CO2 content, and then the melt composition in terms of the 10 major oxides in a predefined order that includes silica, titanium, aluminium, iron, magnesium, manganese, calcium, sodium, and potassium. in the specific order that is listed here and that is also specified in the manual. All the quantities are inputted in international system units, so pressure is in Pascal and temperature is in Kelvin. Water and CO2 are weight fraction, and the volatile free melt composition is also weight fraction, but they can sum up to any number. They don't need to sum up to 1 because those compositions will be rescaled within Solcat. But note that water and CO2 are not rescaled together with the rest. So the silicate melt will be close to 1 by Solcat, and the water and CO2 will stay the same that you have inputted here. SWE, as I told you, some parameters to perform calculation in different ways. The first two numbers indicate the rows in SW.data for which we want the calculations to be performed. KL indicates the type of calculation, and we will see more a bit later. KL parameter because there's different things that Solcat does. IOPEN if the system is open or closed to gas loss. So if IOPEN is 0, there's no gas escape from the system. If IOPEN is 1, there is gas escape, and the latter is defined by the FOPEN parameter, which is next to it, that basically defines the mass fraction of gas phase that is lost at each calculation step in pressure. The two final numbers, Tt and T limit, are used when we want to perform calculation at varying temperatures. And so here is set the temperature step and the temperature limit for this kind of calculation. We will see some more details now when we see all the different types of calculation that we can run depending on the parameter KL. When KL equals to 0, all the conditions are those specified in SW.data. So we have pressure, temperature, water and CO2 that refer to total amounts. So we have a total amounts of water and CO2, and we want to see, and Solcat will tell us how water and CO2 are partitioned among the melt and the gas phase. And this is for KL equals to 0. KL equals to 1 is useful when we want to calculate solubility and saturation curves, because pressure varies from that we specified in SW.data to the atmospheric pressure, and temperature is set. CO2 again refer to top in the multiphase magmas, and then Solcat computes the partitioning at varying pressures of the two volatiles between the fluid and the melt phases. KS2 is calculations performed at varying temperature. So we specified the starting temperature in SW.data, while we specified the final temperature and the temperature step in the SW input.data file, as we have seen with the parameters dt and T limit. Pressure is set, water and CO2 again refer to the total amounts, and Solcat computes the partitioning of the two volatiles between the liquid and the gas phases. Finally, KL equals to -1 is used for kind of an inverse calculation, and in fact, it is used when we have data sets, for example, from melt inclusion. So then temperature is set in SW.data, while water and CO2 in that same file refer to dissolved amounts in the multiphase magma, not to the total amounts, but to the dissolved amounts, which is basically what we can measure in the melt inclusion. Then Solcat, using this input data set, computes the equilibrium pressure. So the pressure that we set in SW.data is meaningless. Solcat computes the equilibrium pressure and the composition of the gas phase that is in equilibrium at those temperature, composition, and pressure conditions. And Solcat produces an output file that includes this information, something more, because it also includes some information on some physical properties of the multiphase magmas that we are looking at. Solcat.out contains one row for each calculation, again, exactly as SW.data. And it gives as a result the pressure, which is the equilibrium pressure when KL equals to -1. Otherwise, it's what we have set in SW.data. Then it will tell you the temperature that we have set, total or dissolved water and CO2, which is again an input that we have set, and then the results begin. So we have dissolved water, dissolved CO2, and then we have fluid composition of the gas phase, water and CO2 at 4%, and then we have the weight fraction of the fluid phase on the total of the multi-phase magma, and also the volume fraction of the fluid phase, calculated using the density that depends on pressure and temperature. And then we have the density of the two-phase magma, of the gas phase and of the melt phase. So this is useful when we want to see how the physical properties varies of these magmas. And then we also have the viscosities expressed in logarithmic units, as it is common for viscosities of magmas. Now, this is an overview of Solcan, how it works and what it provides. In the next couple of lessons, we will go into some more details, and especially we will see how to play with these files and how to use efficiently